In our discussion about exact equations, when we try to solve certain types of differential equations, we want to write the ODE, the differential equation, in this format here. So if we can, then this expression here is our m, and this expression is our n, and we need to verify whether the mixed derivatives are equal. So we need to verify whether partial m partial y is equal to partial n partial x. In other words, we need to verify this, right? This is partial m partial y. We need to verify if it's partial n partial x. Okay? Partial f partial x, that's m, and then when we do partial y, it becomes that. Partial f partial y, that's n, and then when we do partial x, it becomes partial n partial x. If those two are equal, then we can move on. So this is an exact equation. So this will come from function z, right? So we have this becomes a dz of some function z. So we can set the equation in this format and then solve it. The problem is when these two are not equal. So let's see what to do when these two are not equal. Yes, here's an example. So we try to write the differential equation in that format, the nice format. So this expression here is our m, and this is our n. So let's verify that. Partial m partial y, that is derivative of xy with respect to y, that's simply x. Now, partial n partial x, so that's the derivative of this expression with respect to x. So this would be 4x. And 3y squared, that doesn't have any x, so the derivative is 0. Negative 20, the derivative is 0. So here we have, this is not equal to that. So there lies a problem. So at this point, we cannot say that this is an exact equation, and we can't use that method of solving the ODE because that doesn't come from a dz of some z. Well, in many cases, there is a way to deal with that, which is to multiply both sides of the equation by a special factor in such a way that then the new expressions that we get here and here will become, when you take the mixed derivatives, then they will be equal to each other. So this is the idea. So let's go back here to the general equation. So here we have m, right, and then dx, right? So that's the format. And here is the n, a function of x and y, dy. So if the mixed derivatives are not the same, then we need to multiply both sides of the equation. So let me copy that. Okay, so this is not working. Okay, let's try it this way. So we multiply both sides by a function mu. Now this is a Greek letter, so I think you probably know what this is. So this is called mu. It's not am. It's a Greek letter. It's the same notation that we have in the book. Okay. Okay. So we multiply both sides by a function mu, an expression mu. So that will become, so mu times, then here's the function m of x plus, because we multiply everything by mu, then we get that. And then on this side, of course, we multiply both sides by mu, but this side is 0, so it becomes 0 anyway. So that is our new m, okay? So it's called new m. And here's our new n. Now at this point, we have no idea what that mu function is. So let's enforce what we want. What we want is to make sure that the mixed derivatives are equal. So we want to make sure that when we take the partial y of that expression, we want to enforce that and make it equal to partial x, partial derivative of that expression, and with respect to x. So we enforce that. And when we do that, let's see what we get. So we're setting up an equation where eventually we'll be able to find what mu is. Okay, so now this is derivative of a product, right? So here's a product. So derivative of a product is derivative of the first times the second plus the first times derivative of the second. Now, I'll just use the notation, when we have partial mu, partial y. To make it simpler, let's use the notation, the subscript, okay? Mu y. So this means derivative of mu with respect to y. So we're taking derivative with respect to y. So this would be mu y times m plus mu times my. That's this side. And then here we're taking derivative with respect to x. So this is mu x times n plus mu times nx. Okay. Now the problem is that this is an equation where we can find mu, but it's a partial differential equation, right? See, we have derivatives of with respect to y and the derivatives with respect to x. It's very complicated. We don't have it enough to be able to solve this type of differential equation. So what we're going to do some assumptions to simplify the problem. And so most of the, or pretty much all the ODEs that we solve with the exact equation method, we'll be able to do that. So our assumption is that we can assume that the mu function, that mu guy, we can assume that that is a function of let's rewrite this. It's either a function, so that's what I'm trying to say. It's either a function of x or a function of y. And this is very important because otherwise we wouldn't be able to solve it. Okay, and this is what happens if mu is a function of x. So let's look at the first case, okay? So it's case number 1. We have to check and see, look at both cases. Whichever case we find it easier, then that's what we're going to use. So case 2, it's this one. So let's look at case 1. Case 1 is when mu is a function of x only. Okay. So let me put that here. Function. Mu is a function of x only. So look at what's going to happen. So let me copy that down here. If mu is a function of x, then look at this guy here, partial mu, partial mu, partial y, right? Derivative of mu with respect to y, that is 0. That becomes 0. And then we get m plus mu times my, and then partial mu, partial x. This is not 0 because it's a function of x, so this might be some expression in terms of x. Okay, so if you look at that, that's something that is familiar. So all I have to do is, let's move everything to the other side. So I'm sorry, I put m here, but it's 0 times m, right? So this should be, the whole thing here is 0, right? So this is equal to 0. Okay, now let's rearrange the whole thing here. Move this to the other side. Then we get, okay, mu x n, so mu nx minus mu my equals to 0. I'm just rearranging that. And look at this guy here. N plus nx minus my mu equals to 0. Okay. Well, that becomes a linear equation. So this pretty much, if you recall, this is like d mu dx, right? And let's put n over here. So we solve this using the linear equation method. And that's something that we learned. So it's an ODE, it's a regular ODE. So at this point, we're still trying to find that special mu, and we're gonna solve this ODE so we can find the mu, right? Okay, let's clear this. Let's divide both sides by n. I need to have a clean derivative here. So this is d mu dx plus divide by n here. So you remember how we solve this expression? This is our p of x, right? And then we need that special guy, special factor, e derivative integral of p of x dx, right? So here's p of x. So if you remember the development, we're gonna multiply both sides by that special factor, and then eventually we're gonna get derivative of a product times mu. We're solving for mu here. And then here is e integral times the right hand side, which is 0, so that becomes 0 anyway. Okay, so this becomes 0. So mu is, well, we integrate, right? E integral p of x dx is integral, so this is 0, it's integral of 0, which is a constant. Okay, so that means mu is a constant divided by e dx. Now let's put p of x here. This is c divided by e integral. Remember what p of x is? It's nx minus my. Nx minus my divided by n. Okay. Well, we can move this up by switching the sign of the exponent. So negative nx minus my over n dx. And we can move the negative inside if we want. So this is c, e. And here we can move the negative inside, and then we just flip that, we switch that. It becomes my. So let me write this clear here. It's my minus nx divided by n dx. So there it is. There we go. We have an expression for the mu function. Now, since this is an integrating factor, we can pick, let's pick c equals 1 for now. It will work with any constant, right? That integration factor works with any constant. So we can pick c equals to 1 just to make it simpler, okay? And then, so that's the expression. Whatever that is, so all we have to do is to integrate that, and we get our mu. Now, the second case, I don't know if you recall that. Let's go back here. So if mu is a function of x, then we get that expression. If mu is a function of y, if you do a very similar thing, it will get an expression for mu again that's kind of similar to this one. So let's put that here. Case 2 is when mu is a function of y. Okay. Mu is, looks like m. Mu is a function of y only. So that's the second case. Then if you do the same development, same type of development, eventually you will get mu equals to c e, and then I'll write that here for you. Integral of nx minus my divided by m dy. And then again we pick c equals to 1. Okay, summary. Now, I don't think you want to develop, derive all of that. I think it would be better to memorize these two integrating factors. So we have case number 1. So if you think the mu is a function of x, then the integrating factor is mu equals to e integral of my minus nx divided by n dx. If you think that mu is a function of y, then mu is e integral of nx minus my divided by m dy. So that's the conclusion of this part. So it looks pretty complicated. So let's go back to the original example. So let me go grab the example here. Here it is. So let's go back to here. Okay. Back to the example. So remember how we had these two m and n, and it didn't work. So now let's take a look at the integrating factor. So we're going to work these expressions here, see these expressions and see how they look like. If this expression has only x, then we know that we are on the right track. If this expression has only y, then we know that we are on the right track for case number 2. Let's take a look. Let's check. Okay, here is my minus nx divided by n. So let's see what that is, okay? This is our old m, right? This is m, and this is our n. So my, that's x, right? Partial m partial y, that's x, minus, and then derivative of that with respect to x, that's 4x divided by n. Now n is 2x squared plus 3y squared minus 20. So if we look at this, this is not a function of x only, not a function of x only. So we cannot use it, unfortunately. Well, now let's check the other case, case number 2. Hopefully it will work. Case number 2 is nx minus my divided by m. Okay. So nx is 4x, right? It's derivative of that with respect to x, minus derivative of that with respect to y, divided by m. M is xy. Okay? Okay, so this is 3x, xy. This is 3 over y. There we go. That is a function of y only. So we can use it. So that means we can use, so we use case number 2. Okay. So if we use case number 2, then we know that our mu is e integral of nx minus my over m dy. So, and we already have that expression here, it's 3 over y dy. So this is e to, this is 3 ln y. Okay. And now it looks like we can cancel the e with the ln, but we have to do something before we do that. We have to do something here, get rid of this 3. We can move 3 inside, right? It's multiplying. So it's multiplying, we can move it inside. So we can do e raised to ln of y cubed. Well, now the e and the natural log cancel, so this is y cubed. Okay? All right. So that is our integrating factor. So we can use that, multiply both sides of this equation by that factor. So let's do that. Yeah, okay. Here it is. So y cubed, multiply both sides by y cubed. So we get x, y cubed dx, plus, and then whatever that is, 2x squared y cubed plus 3y to the 5th minus 20y cubed dy equals to 0. All right, that's just to get us started with the exact method. Now we can use the exact method. And just to show you how this works out, let's check the mixed derivatives again. So this is our new m. This is our new n. Okay. So let's check partial m, partial y. So that's 3 x y squared. And that's that. And then partial n, partial x. Well, here it's partial x. That's 4. So let's put that in there. Okay, that's 4 x y cubed. And then here, partial x is 0 because there's no x in here. And let's see. I think I'm missing something there. Let's see. Yeah, I am missing something. And it's right here. This should be 4, not 3, right? Y cubed y is 4. Okay, let's put that here. It's 4. There we go. Now it's equal. So 4x cubed, 4xy cubed, and then on this side, partial n, partial x is 4, right? 2 times 2, 4x, and then y cubed. And then the other two expressions here don't have x, so the derivative is 0. So now we can continue. And with the exact method. Exact equation method. So I'll let you finish that. So that's just like we did before. So you have to continue to finish solving the ODE.